Ladies and gentlemen, now we will start the first lecture of the Improve Phase module. Where are we? All data of the process and diagrams have been analyzed and checked for their effect on manufacturing system process, quality, and production. We found out the cause of any problem or issue in order to solve it, and using different tools of the improved phase for the whole process. During the improved phase, we will improve and evaluate solutions, implement variation reduction, standardize process, and assess the risk factors. The module will be divided in 8 lectures. It includes the following documents and videos for download, the course material in PDF, templates for push-pull, tack time, FMEA, 5S's audit checklists, and VUT calculator. Instructional videos for FMEA, Sigma XL, process load balance Sigma XL, and FMEA, Minitab. TRIZ 40 Principles PDF file. During the module, the following topics will be covered: process lean metrics, 5S's, creativity techniques, setup reduction, generic pull systems, replenishment pull systems, minimum safe batch size, total productive maintenance, mistake proofing and prevention, work cell optimization, improved process balancing, production leveling Hijunka, visual process controls, failure mode and effects analysis, implementation planning. During the first lecture, we will cover process lean metrics. Process consists of a set of workstations. Units are processed sequentially, one at a time. Process flow and value stream are from workstation A to E. Any manufacturing system consists of value chains or process chains. Each process chain consists of processes, while each process consists of many workstations. Each complete workstation consists of many tasks. Cycle time is the time a workstation or a process can produce a unit of output. It is interval of time between two successive outputs coming out of a workstation or process. For example, for a process consists of 5 workstations. The following are the cycle time of each workstation. For workstation A, the cycle time is 2 minutes per unit. And for workstation B, the cycle time is 3 minutes per unit. And for workstation C, the cycle time is 5 minutes per unit. And for workstation D, the cycle time is 1 minute per unit. While for workstation E, the cycle time is 4 minutes per unit. Capacity is the number of units a workstation can complete in a unit of time, which is equal to 1 over cycle time. For workstation A, the cycle time of 2 minutes per unit leads to the capacity of 30 units per hour. For workstation B, the cycle time of 3 minutes per unit leads the capacity of 20 units per hour. For workstation C, the cycle time of 5 minutes per unit leads the capacity of 12 units per hour. For workstation D, the cycle time of 1 minute per unit leads the capacity of 60 units per hour. For workstation E, the cycle time of 4 minutes per unit leads the capacity of 15 units per hour. The bottleneck is the workstation with the longer cycle time and the lower capacity. Workstation C has the longest cycle time and the lowest capacity. Workstation C is the bottleneck in our process. Throughput rate is the actual output rate of a process or workstation that produces output. The maximum throughput rate of a process or workstation is its capacity. Lead time is the time a unit takes to go from the first to the last workstation. Lead time is equal to workstation cycle times plus waiting times, which is equal to 15 minutes in our example. Any process passes with several steady states during its transient to final steady state. For our process, during the transient to steady state 1, the throughput of workstation A is 30 units per hour. The throughput of workstation B is 20 units per hour. The throughput of workstation C is 12 units per hour. The throughput of workstation D is 12 units per hour, which is less than or equal to the previous station. And the throughput of workstation E is 12 units per hour, which is also less than or equal to the previous station. Now, station B can accept only 20 units per hour, so WIP will start to build up after station A. After some time, station A will not send units to B, except what B can handle, which is 20 units per hour, so WIP disappears between A and B. For our process, during the transient to steady state 2, the throughput of workstation A is 20 units per hour. The throughput of workstation B is 20 units per hour. The throughput of workstation C is 12 units per hour. The throughput of workstation D is 12 units per hour. The throughput of workstation E is 12 units per hour. Station B will not produce more than what it can get from previous station A, and so the rest of the stations. At steady state, all stations will have a throughput which is equal to the capacity of the bottleneck station C. The throughput of all workstations is 12 units per hour in steady state 3. As a last steady state, the final process capacity is 12 units per hour for all stations. So, the final process cycle time will be 5 minutes per unit for all stations. Utilization is the final throughput divided by the workstation capacity. The throughput of any workstation is less than its capacity, except at the bottleneck station. Utilization of workstation A is 40%. Utilization of workstation B is 60%. Utilization of workstation C is 100%. Utilization of workstation D is 20%. Utilization of workstation E is 80%. Workstation cycle times are 2, 3, 5, 1, and 4 minutes per unit, while process cycle time is 5 minutes per unit. Utilization is equal to sum of workstation cycle times divided by the sum of the process cycle times. Process direct labor utilization is equal to 15 divided by 25, which is equal to 60%. Process direct labor utilization is equal to the lead time divided by the process cycle time multiplied by the number of operators. Process direct labor utilization is equal to 2 plus 3 plus 5 plus 1 plus 4 divided by 5 times 5, which is equal to 60%. The wait time is equal to the process cycle time minus workstation cycle time. The table shows the data of each process, the cycle time, wait time, process cycle time, and utilization. It also shows the total cycle time of the all stations, or lead time, the total wait time, the total cycle time of the process, and the process direct labor utilization. The bar chart shows the work time and the wait time for each workstation and for the process, for comparison. Work in process, WIP. It is the average number of units inside a process being worked on or waiting between workstations. The number of customers inside a service station being served or waiting to be served. WIP is an inventory inside the process to differentiate it from the external inventory. We can use Little's law to determine the WIP. According to Little's law, work in process is equal to the throughput rate multiplied by the lead time. However, applies only to stable processes, steady state, where the rate of input and output are the same, stable. Usually a process moves from a transient to a steady state. WIP exists mostly between the slowest workstations. Throughput is equal to 12 units per hour. Lead time is equal to 15 minutes. WIP is equal to 12 times 15 divided by 60, which is equal to 3 units. Utilization is equal to the WIP divided by number of workers, which is equal to 60%. Consider a simple packaging line with 3 processes, as shown in the table. Please calculate 1. Throughput of the line, 2. Line efficiency, 3. Net throughput of the line. 4. Adding an accumulation table, buffer, between the filler and the labeler, the line is broken into 2 separate systems. This breaks the compounding effect of the machine efficiencies. Recalculate all the above. 6. If the line is broken into 3 sections, with each machine running independently. So, no compounding of efficiencies. Recalculate the above, and the increase in line efficiency. Please pause the lecture and solve the exercise. 1. Throughput of the line is restricted by the slowest process. For example, labeler the throughput is equal to 200 parts per minute. 2. Net efficiency of the line is calculated by multiplying the efficiencies of each machine in sequence, which is equal to 83.9%. 3. Net throughput is equal to 167.7 parts per minute. 4. Net efficiency of the line is equal to 89.2%. Net throughput is equal to 178.4 parts per minute. 5. No compounding of efficiencies, so the lowest net rate of the machines is equal to line throughput, which equal to 194 parts per minute. Line efficiency is equal to 97%, with a 15.7% increase. What does 15.7% mean to a company's bottom line? If the firm is having trouble meeting market demand for a product, it could be huge. Let's say the line is running 2 shifts per day, 8 hours per shift, 7 days a week, and the profit equal to 50 cents per product. 2 shifts times 8 hours times 60 minutes or hour times 50 cents times 26.3 extra products per minute is equal to $12,624 per day in additional revenue. Over 6 months, it generates $2,203,880. Please perform the activity and send your outputs by email for assessment. Thank you, and see you in the second lecture of the Improve phase.